In section 10.3, we'll review the concepts of resonance, formal charge, and electronegativity trends to refine our Lewis structures. In this lesson, we'll focus on resonance and electronegativity and save formal charge for the next lesson. Let's begin. While Lewis structures help visualize the bonding in molecules, they do have limitations. In some cases, a molecule cannot be represented accurately by a single Lewis structure, but requires multiple structures that differ only in the placement of the multiple bonds and lone pairs. Molecules and ions that have such structures are said to exhibit resonance, and we often draw multiple resonance structures to represent them more accurately. For example, the carbonate ion has 3 resonance structures. The double bond is equally likely to be located between carbon and any one of the 3 oxygen atoms. In fact, the pair of electrons shown as the double bond is shared or spread out among all 3 locations. This is a delocalized bond and is designated as such by the double-headed arrows between the structures, or as a single resonance hybrid as shown on the far right. All 3 carbon-oxygen bonds in the carbonate ion are equivalent and have properties in between those of a single and double bond. Let's build the Lewis structure for the polyatomic ion nitrite. Sum up the valence electrons. We have 1 nitrogen with 5 electrons and 2 oxygens with 6 electrons each. Nitrite also has a negative charge, so we add 1 electron for a total of 18 valence electrons to place in this structure. 2. Select the central atom and arrange the other atoms around it. From the formula, it's a solid guess that nitrogen is going to be the central atom since it appears first. Nitrogen also needs to form the most bonds to gain 3 more electrons as compared to each oxygen that only needs 2 more electrons. 3. Draw single bonds between the central atom and each terminal atom. Connecting the atoms together with single bonds uses up 4 electrons. 4. Distribute the remaining electrons to the outer atoms. We have 18 electrons total to place, and we've used 4 so far, so we need to place 12 more electrons. The outer atoms get lone pairs first, so here goes. We have 2, 4 in bonds, then 6, 8, 10, 12, 14, 16. We still need to place 2 more electrons. Step 5. Assign any remaining electrons. Nitrogen only has 4 electrons around it in the 2 single bonds, so let's add the 2 lone pairs here to give nitrogen a total of 2, 4, 6 electrons. Step 6. Move lone pairs to create multiple bonds if the central atom has less than an octet. Nitrogen is short 2 electrons, so let's pull 1 lone pair of electrons from oxygen to form a double bond. Step 7. Verify duets, octets, and the total number of valence electrons. Let's check each atom. The oxygen on the left has 2, 4, 6, 8 electrons. Nitrogen has 2, 4, 6, 8. The oxygen on the right has 2, 4, 6, 8 electrons, so all octets are satisfied. Counting total electrons, we have 2, 4, 6, 8, 10, 12, 14, 16, 18. This structure represents an ion with an overall charge, so we've enclosed the structure in brackets and indicated the polyatomic ion's charge outside the brackets. Finally, because the double bond has an equal chance of being between either oxygen and nitrogen, we show both possible resonance structures separated by a double-headed arrow. This structure is done. When drawing Lewis structures, considering the electronegativity, or the relative measure of the ability of a bonded atom to attract shared electrons, can help us identify the central atom. The most electronegative element, fluorine, is assigned an electronegativity value of 4.0 and all electronegativity values decrease from there as you move to the left and down the periodic table. It's worth noting that the lighter noble gases do not have defined electronegativity values because they form no bonds. Further, electronegativity values have no units, which is a rare occurrence in chemistry. The more electronegative elements, like fluorine, pull shared electrons closer to themselves than atoms with lower negativity. For this reason, the highly electronegative elements tend to be terminal rather than central atoms. This makes sense if you think about the order in which we assign extra electrons. The terminal atoms are always assigned the lone pairs first, then remaining electrons go to the central atom. Let's look at an example. What if we were given the formula POBr3? Which atom is our central atom? We can either look up the exact electronegativity values, or more likely, think about the position of each element on the periodic table relative to fluorine. We see that oxygen is the second most electronegative element, then nitrogen and chlorine. If you can remember those four elements' electronegativities, that knowledge will serve you well in the coming months. Bromine is still fairly electronegative, but phosphorus has an even lower electronegativity value. Because of the lower electronegativity, phosphorus will be our central atom since it will share electrons more than bromine or oxygen. I'll leave you with the author's parting thoughts for this section. Part 2 will come in the next lecture.